Welcome, class. I'm your lecturer for today, and I am absolutely thrilled to have you here for this explainer. If you've ever stopped to wonder how a simple tap on your smartphone seamlessly loads a web page hosted on a server literally halfway across the globe, well, you're in the right place. Today, we are going to completely demystify exactly how digital devices talk to each other in our IE 1030 Data Communications Networks module. This is Lecture 02, Protocol Architecture. Let's get right into it. So, here is our roadmap for today's explainer. We'll be looking at Section 1, what are network protocols? Section 2, the Wi-Fi 4-frame exchange. Section 3, the need for protocol layers. Section 4, data encapsulation explained. And finally, Section 5, the protocol stack. All right, starting us off with Section 1, what are network protocols? Let's actually define what a protocol is. And honestly, the best way to do this is to think about human interactions. When you ask a friend for the time, you follow this unwritten human protocol. You don't just walk up and yell, 2 o'clock, right? No, you start by getting their attention. You say, excuse me. You wait for them to respond with yes, or maybe just a nod. Then you ask, what is the time? They answer, and you finish the exchange with a thank you. It's a format and an order we all just implicitly agree upon. Well, network protocols do the exact same thing. But instead of humans, we're talking about computers, smartphones, routers, and switches. These protocols govern absolutely all communication activity on the internet. So formally speaking, a protocol strictly defines three things: the specific format of the messages, the order in which those messages are sent and received among network entities, and the exact actions taken after a message is sent or received. Now, for our first-year IT students here, you definitely want to remember this term. In networking, a message exchanged using a protocol is formally called a protocol data unit, or a PDU. The protocol dictates exactly what a valid PDU looks like and how a device should react when it gets one. But here is a really crucial question for you to ponder. What if a computer sends a message and hears absolutely nothing back? Just crickets. Or what if one device responds in Greek, but the other only speaks English? In human protocols, that just gets awkward. But in network protocols, we have very specific contingency plans. If an expected response isn't received within a precise time frame, something called a timeout occurs. The protocol explicitly tells the machine what to do next in that scenario, which is usually to just try sending the message again. Okay, moving on to Section 2, Wi-Fi 4-frame exchange. This brings us perfectly to a real-world networking example, how Wi-Fi actually works behind the scenes. Imagine you're in a really crowded, noisy room. If everyone speaks at exactly the same time, it's just chaotic noise, right? In networking, we call that a collision. So before speaking, you follow a polite protocol. First, you wait for a moment of quiet. Then, you clear your throat to ask for attention. You wait for someone to give you a nod. Then you confidently speak your piece. And finally, you look for a thumbs up that your message was actually understood. And this brilliantly illustrates that exact human process translated into what we call the Wi-Fi 4-frame exchange. Say your laptop, the source, wants to talk to your wireless router, the destination. First, it sends an RTS, which stands for Request to Send. It's essentially clearing its throat. The destination replies with a CTS, or Clear to Send. That's the nod. Only then does the source actually transmit the data. And finally, the destination responds with an ACK, an acknowledgement frame, basically giving a thumbs up saying, I got it safely. Now, what is super interesting here is the precise timing involved. Before even asking to send that RTS, the device waits for a DIFS, a distributed interframe space of 34 microseconds. It's just listening to make sure the channel is totally clear. But notice the waiting time between the RTS, CTS, data, and ACK. That's a CIFS, a short interframe space of just 16 microseconds. So why is it shorter? Well, because once the conversation has started, we want to give this ongoing exchange priority over any other device that's waiting to start a new one. All the other stations in the network hear that RTS and CTS, calculate exactly how long the exchange is going to take, and politely keep quiet. And if that final ACK never arrives, boom, a timeout triggers and the sender starts the whole process over again. Let's look at Section 3, Need for Protocol Layers. So, we have all these highly precise timing rules, complex addressing schemes, error-checking mechanisms. How on earth do we organize all this complexity without it turning into utter chaos? The answer is protocol architecture. Communicating across a global network is a massive, incredibly complex task. So the core principle here is breaking that impossible task down into a number of smaller, highly specialized subtasks. We assign each subtask to a specific layer in a stack, where each layer only has to worry about its one specific job. To really make sense of this concept, let's look at a relatable real-world example, the office analogy. Imagine a large corporation where communication is handled across three distinct hierarchical grades, or layers. You have the officer layer, the secretary layer, and the assistant layer. In this setup, an engineer who wants to send a design document doesn't personally walk the letter over to another building. They just write the message, that's the officer layer's job. Then they hand it down to the secretary layer. The secretary figures out the formatting, puts it in an envelope, and addresses it. The secretary then passes it down to the office assistant layer, whose only job is to physically deliver it to the other office building. When it arrives at the destination, the whole process just reverses. The assistant hands it up to the secretary, who opens the envelope, and then hands the memo up to the receiving engineer. The critical takeaway here is that each specialized layer provides a service to the layer directly above it, and uses the services of the layer directly below it through very clear defined interfaces. Which leads us to Section 4, Data Encapsulation Explained. Let's see how our office analogy builds into a really fundamental networking concept called data encapsulation. Consider the difference between normal and confidential office communication. If the finance officer wants to send a top-secret financial report, they write it and pass it to the confidential secretary. Now, this secretary doesn't just put it in a normal envelope. They might encrypt the text and put it inside a special bright yellow confidential envelope. They attach instructions on the outside, who it's from, who it's for. Then the office assistant takes that envelope and physically moves it. The crucial point here is that this process of wrapping the original data inside protective, instructional envelopes as it moves down through the layers is exactly what we call encapsulation. Honestly, think of it just like Russian Matryoshka nesting dolls. The innermost doll is your actual application data, say a WhatsApp message. As it gets passed down the network stack, the next layer puts it inside a slightly larger doll, which is a new header with routing instructions. Then the next layer puts that doll inside an even larger doll, adding MAC addresses. At the receiving end, the process is perfectly reversed. This is called de-encapsulation, where the computer unpacks each doll layer by layer until the original message is revealed to your friend. Section 5, the protocol stack. Now, we are ready to take those analogies and apply them to real computer hardware. Here is the actual 5-layer Internet Protocol architecture, known as the TCP/IP suite. Now, some of you might have heard of the OSI model, which actually has 7 layers. The OSI model adds a presentation layer for data formatting and a session layer for managing dialogues. But in the real world, the TCP/IP 5-layer model just handles those functions neatly within its single application layer. Now notice how layer 5 on host 1 logically communicates directly with layer 5 on host 2. But physically, the data travels all the way down the stack. It passes through intermediate devices, specifically switches, which only process up to the link layer, so layer 2, and routers, which process up to the network layer, layer 3, before traveling all the way back up the stack on host 2. I highly recommend grabbing your pens and taking detailed notes here, because this table maps exactly how encapsulation creates our protocol data units. It starts at the very top. The application layer creates a message. It passes it down to the transport layer. The transport layer, using protocols like the reliable connection-oriented TCP or the fast connectionless UDP, adds a transport header. We now call this new PDU a segment. Down it goes to the network layer, usually the IP protocol, which adds a network header for global routing, creating a datagram. Then down to the link layer, like our Wi-Fi or Ethernet, which adds a link header to create a frame. Finally, the physical layer turns that whole nested frame into raw ones and zeros, bits, to blast over a copper wire, a fiber optic cable, or through the air as radio waves. And this brilliantly illustrates why protocol architecture is just a masterpiece of engineering. The true brilliance is modularity. Because each layer has a strict, standardized interface, you can completely upgrade the physical hardware at layer 1, like, say, swapping an old copper Ethernet cable for a brand new Wi-Fi 6 router, without having to rewrite a single line of code for the web browser sitting all the way up at the application layer. As long as the interface between the link layer and the network layer stays exactly the same, the entire stack functions flawlessly. It's a real game changer. Let's move into our conclusion and recap. All right, we've covered a ton of ground today. Let's do a quick recap to ensure these fundamental concepts have truly sunk in. We've explored how network protocols are the absolute law of the land, dictating the rules, format, and order of communication, much like a polite human conversation. We saw how data is meticulously encapsulated into PDUs, transforming from messages to segments to datagrams to frames and finally to bits, as it travels down a 5-layer modular stack. And we discussed how mechanisms like specific waiting periods and timeouts keep the whole system moving even when the network gets congested or noisy. Before you pack up, I'm going to leave you with a final, provocative thought to really test your understanding before our next lecture. Think back to that Wi Fi 4 frame exchange. If a timeout actually occurs because an ACK never arrived, what exact physical or logical scenarios could have caused that data packet to just vanish into thin air? Was there physical interference? Did a router get totally overwhelmed and drop it? And more importantly, according to the protocol rules we just discussed, what exactly should your computer's transport layer do to recover from that loss? Think about it. Thanks for joining me for this explainer, and I will see you all in the next lecture.